Okay, thanks. So let's see, I'm using this, right? Okay, so while I'm going to basically try to give you a handful of interlocking themes, tightly interlocking themes, and take you through some of, or all of these things will get mentioned somewhere in there. Occasionally, I will tell you, of course, about things about where we're in the dark when we come to BSM physics, and so we have some intuition, and we have a number of case studies and examples, and there are lots of places where I would like to understand more, and I presume you would too, and I'm sort of going to put this yellow question mark to just say that, so you can watch out for where I think there is stuff to be done in the next decade. So let's just get started. So one of the first of these interlocking themes is the origin of the hierarchies. I should say many of these things that I'm talking about are familiar to you and you've heard talks on them, and I would ask, forget everything you know so that you're looking at it afresh, which is the way that you're going to have to do it to make a case to the outside world and even to all of your peers about the way you want to go forward in this field. So from scratch, we see, yes, fundamental physics is certainly a world of hierarchies. And so it's puzzling where these hierarchies came from. Are there mechanisms behind that? And here is a classic role for non-perturbative effects in physics. And to exemplify it, I give this famous formula of dimensional transmutation in asymptotically free theories like QCD, where we can understand the proton mass or why the proton is so light, understand it in terms of this exponentiation, which is to say that if we have at the high scale, the fundamental parameter, the strong coupling at the Planck scale being a little bit modestly small, we can exponentiate that smallness into the incredible smallness of the proton mass. That's what I mean by a satisfactory answer to the question of why is there a hierarchy, okay? So I don't want to make it a legal document. I just want you to smell it like you smell your coffee in the morning and say, this is good. I wish there was more of this in my understanding of all of the hierarchies of nature, okay? So let's see what we know already. Composite Higgs theories are literally taking that kind of idea and saying that there are composites, like the Higgs boson itself may be a kind of composite, and the formula may be very much like what I just said, okay, a replay of what we've seen. And this compositeness scale sets the natural scale for the weak scale, et cetera, where at my first pass, I'm being very sloppy about order one things like this, which matter a lot to experiments, okay? We can also turn to supersymmetry. Supersymmetry, of course, comes with, you shouldn't forget it, a profound new relativistic symmetry. I would even say quantum relativistic symmetry. So it'd be an incredible discovery, okay? Even worth a 1 in 100 chance of discovery, but that would be worth humanity pursuing it. Again, supersymmetry breaking in supersymmetric strongly coupled theories, or non-perturbative effects in such theories, would look very similar to what we just saw in the QCD case, where supersymmetry breaking would be like chiral symmetry breaking in QCD, okay? So it can happen dynamically and spontaneously. And then if it happens in some other sector, so-called hidden sector, it might get mediated to us through, say, for example, Planck scale suppressed effects, where the superpartners in our sector, the standard model, are all comparable to sort of this going rate gravitino mass. And again, that basically sets the natural size for the weak scale, the Higgs mass, the W mass, and so on. The other mechanism that we have, sort of general purpose mechanism for producing hierarchies, are called warp compactifications of higher dimensions. They've been studied in effective field theory as well as in string theory, and they're a very robust way of generating hierarchies. But now these hierarchies are seen to have a geometric origin in terms of redshifts, very analogous to the kinds of redshifts we see in cosmology as a function of time, but here as a function of an extra dimensional coordinate, okay? Theories built along these lines are ADS-CFT dual, so they have a kind of dual grammar of 4-dimensional strong coupling, okay? So similar to the compositeness theme, and in some sense in the same universality class as that, but they're more pragmatically treated in this extra-dimensional language because by ADS-CFT, the strong coupling problem, which is thorny, is traded for a weakly coupled theory in the dual, albeit a weakly coupled theory which involves emergent extra dimensions. Okay? So this is another way in which we can pursue the question of hierarchies, and it's led at the sort of most pragmatic level of the weak scale to RS1 models, the warp standard model in some way. And again, the Kaluza-Klein excitations, the new physics of these extra-dimensional theories, are given by formulas similar to what I showed you, but again, a modest hierarchy, in this case, a modest hierarchy between a 5-dimensional scalar mass and the 5-dimensional Planck scale, gets exponentiated into an incredibly small hierarchy, say, between hopefully the weak scale and the Planck scale. Secretly dual to non-perturbative effects in strongly coupled field theories. Okay, so these are general purpose mechanisms we already have some idea about. But then we have to say, there is a little highway. I don't want to put my head in the sand about anything, okay? I don't want to ignore any complication that real life is throwing at us. And one of those complications is we ain't seen nothing beyond the standard model yet, okay? So what are we supposed to make of it? Well, in these theories, the weak scale is sort of set by the scale of new physics, Kaluza-Klein excitations of warp compactifications or superpartners. And it's basically set by some sum of terms of order, the new physics scale times some loop factor. But if we look at explicit searches for these new physics particles, for example, the gluinos of supersymmetry or the Kaluza-Klein gluons of warp compactifications, we find that we are in multi-TeV terrain already just by the searches we've done, and also comparable bounds through the study of precision electroweak tests from the LHC and prior to that, and precision Higgs tests at the LHC already, okay? So there's a problem. The puzzle is simply this, that it seems like you would that the going rate for the weak scale, according to this formula, is given by roughly the scale of this new physics, and we haven't seen this new physics already into the multi-TeV regime. So what are we to make of that? Let's just go through logically what it could be. If indeed these new states are constrained by experiments to be in the multi-TeV range, then the only way to make sense of this equation is that there are chance calculations in this chance cancellations in the sum. And the cancellations have to be at the 10 to the minus 4, 10 to the minus 3 level. Okay, that's the face of the hierarchy problem or the little hierarchy problem. So that's possible. It's possible. Stuff happens. It's a strange, strange world. You could have a chance cancellation. Or there's some non-minimal structure that goes beyond the mechanisms, the general mechanisms I've just mentioned. So keep that thought in mind, okay, as the talk goes on. The next thing I want to say is that we actually have, so I'm saying this because in the modern world, the current era that we're living in right now, 2022, this doesn't get discussed a whole lot. So I just want to remind you that we actually have some set of comprehensive and panoramic models of particle physics that seem to incorporate all the different things that we know have to happen. So let's take a quick look just to remind ourselves, okay, and hopefully more to come, okay. So here is a supersymmetric theory, one which in the end I kind of find myself admiring the most of the supersymmetric theories. It's called Gaugino-mediated supersymmetry breaking, and basically it's supersymmetry, but it involves an extra dimension again. The extra dimension is very tiny. Its length is smaller than the gut length, okay, so it's really, really tiny, not directly experimentally relevant. And the main thing is it allows the neck of the woods in which supersymmetry is broken to be sequestered from the place where we put standard model matter, including flavor breaking and CP violation, okay? In doing that, in sort of keeping the flavor and CP violation away from the SUSY breaking and hence the soft supersymmetry breaking masses that the standard model inherits, one finds that the only sources of flavor and CP violation in this theory are the Yukawa matrices of the standard model itself. you don't introduce any new flavor violation, which means the Jim mechanism, the beautiful Jim mechanism of the standard model, is intact. That is an enormous achievement for any physics that goes beyond the standard model, because as you know, flavor tests in principle would take a completely random DSM theory and kill it, even if it was sitting at 10,000 TeV. Okay, so these theories have magical properties along the lines that we would need if they were just around the corner. I like gaugino mediation in particular because it also solves a thorny self-inflicted problem of SUSY called the mu problem in a very simple way, compatible with the flavor properties. Okay, but even here, there's something interesting with flavor experiments. Because when you have supergravity in the bulk, or gravity, you're going to need some sort of UV completion, and that would be given by something like string theory. Whether it's string theory or something else, there would be some very massive states that have to live in the bulk as well. And they give a way of communicating the flavor and CP violation here to the SUSY breaking over here through these Yukawa suppressed effects, where the heavy particle is not very efficient at communicating between the two. But what it can do is it suddenly introduces new sources of flavor and CP violation in the SUSY breaking parameters of the MSSM or the SSM. This would give small, so not ruled out today, but potentially observable signals in flavor changing neutral currents, electric dipole moments, and so on. So this frontier of flavor and CP violation as an experimental frontier is extremely important. It may be a discovery, a first discovery direction, even before colliders. We don't know. Okay. So another question on our mind. So I'm trying to ask questions rather than saying they're legal money-back guarantees, because we don't get those kind of things in physics. But we can ask interesting questions. So one is, what is the origin of the flavor hierarchies? If anybody's looked at the quark masses and the CKM angles, and you looked at how they look, you would say something is going on there. That is not a bunch of random numbers. There's a story behind that. But what is that story? The standard model doesn't tell us. This is an example of a theory of flavor, if there are others. This is in a warped five-dimensional model, where the different wave function overlaps give rise to flavor structure in the Yukawa matrices in a rather attractive kind of way. The wave functions themselves come out of kind of the random draw of the parameters of models of this type. But one gets attractive kind of structures in the Yukawa matrices. They are ADS-CFT dual to this concept of partial compositeness, where mass eigenstates are superpositions of elementary particles and composite particles. Okay, so it's a very broad, robust, interesting direction. But I want to ask the experimental question. How close can the origins of flavor and CP structure, how close can they be to us as experimentalists? The answer, for example, are they basically all ruled out if they don't live at 10,000 TeV or 100,000 TeV? No, the answer is surprisingly close. They could be surprisingly close to us, just given the following facts. That models of this type, these warp models, have a kind of Jim mechanism. It is not it's very powerful. So it protects you from current observations of flavor violation up to some degree, but it's not perfect. And generically, if you take models of this type and you don't try to play too many games in parameter space, the new physics, the Kaluza-Klein excitations, are of order tens of TeV, bounded in that way, which is something humanly achievable. We could go there. We could build colliders that can see this kind of physics. So it's an amazing thing to me that something as tricky as flavor structure, which normally you might think is throwing out flavor signals all over the place and it's all ruled out, could actually be very close at hand. And if there are other mechanisms, they may even lower this further. That's an open question. Changing topics. Another theme that I want to talk about, and we'll pull everything together at the end, are what I'll call the control knobs of the universe, which easily defined are just scalar fields whose vevs determine the couplings, in even renormalizable couplings of effective field theories. So the classic example is the Higgs itself is a kind of control knob. In QED, their electron mass is a constant of nature, but in the standard model, it is the vev of the Higgs that is setting this constant of nature, okay? In QCD, there's a theta angle, which happens to be incredibly small according to experiment, but that theta angle in the theory extended to include the axion is really the result of the axion vev dynamically adjusting in order to predict that the theta angle in the renormalizable theory is zero, okay? So these are familiar examples, but when you go to more fundamental theories, which are either extra-dimensional or string theory, you find that the idea of such control knobs are seemingly quite typical. For example, radions or moduli, where a higher dimensional theory, when viewed at low energies, one can just integrate the extra dimensional size. In this case, let's say it's a circle, 2 pi times r, and that forms an effective 4-dimensional coupling. The size of the extra dimension is a 4-dimensional coupling, but the size of an extra dimension in a theory of gravitating space-time is dynamical. It's effectively a field. So when I say the radius of the extra dimension, it's really the vev of a radion field. So that's an example of a modulus or radion that happens a lot in our top-down thinking. And these moduli can play profound roles in physics. They've been things that one can certainly look for. They may mediate macroscopic forces. They may underlie some aspect of dark energy. They have shown up in particle physics models like the relaxion. So these are control knobs that really may guide why the universe looks the way it looks. Of course, you'd love to search for them. And it may be hard to create the phi. The vev is somehow already baked in. But to see the fluctuations may be hard. If you even think about the Higgs, thinking of the Higgs as a control knob of the universe, its discovery took till 2012, and it was an incredible achievement, right? So these phis, they might be light. They could be things like axion dark matter. They could produce light, they could be light moduli fields and so on. That's one direction of super light, super weakly coupled control knobs. Or they could be heavy. For example, in a kind of middle zone, the radion of the RS effective field of the RS theory would be a Higgsish kind of discovery that could be made at colliders. Or they could be vastly heavier than that, in which case you might start to worry that all you'll ever see are their vevs. So before going into that, we should ask who controls these controllers, okay? And the answer, of course, is they're controlled by their effective potential, right? Now, the effective potential is there in blue. There's the minimum. There's the vev, and whatever the theory that fields this vev is then given this effective coupling based on what that vev is. Okay, so again, you've seen examples of this. The CP axion. Here's my very crappy way of writing the potential. And we see QCD is sculpting a potential for the axion. That's who controls the axion. In models of radiative electroweak symmetry breaking, such as in the MSSM, it's the partners and superpartners whose radiative corrections are sculpting a potential for the Higgs. Okay, but in general, for any of these other moduli or heavy scalars and so on, it may actually have multiple minima. And so imagine a space in which there are multiple fields. There may be multiple scalar fields out there, and they may have multiple minima of some more complicated effective potential. And now each of them may represent, in this multidimensional field space, each of them may represent a place which could be called a vacuum, and that if you put yourself there, you would live there for 10 billion years, okay? In which case, the effective field theory that is controlled by each of these vevs would be a different effective field theory. There'd be a sort of discrete set of choices, but it could be a huge number of such different vacua, all with giving rise to different low energy effective field theories, okay? Good. Now it seems like it's either this one or this one or this vacuum, but it could be all of the above. For example, you could have excited states of this effective potential, which are really going between, as a function of space or time, going between one extremum or another extremum or another extremum of the effective potential with some domain wall transitions between them. And in the presence of inflation, these domains where one effective field theory or another effective field theory rules or governs at low energies could be vast superhorizon. So our entire universe may be locked into just one domain, and it looks like a constant of nature in this region, but it's not. Ultimately, it's not. Okay, so we have these effective field theory domains in a large multiverse. Okay, so there, I've said it. Sorry? Thank you. Good. So I have to raise this question. I said all dirty laundry gets aired now. So here it is. There is the Anthropic Principle, which in the language of that multiverse I just showed you on the previous slide is just, where do you place yourself? Do we live here, or do we live here, or do we live here? I don't know, a priori. But we know that there must be an observer bias, because there has to be an observer bright enough to ask such questions. Okay. So apparently, it's a reasonable guess that we might need our ability to observe this, which domain we live in, first has a prerequisite that the cosmological constant here is small enough so that we can have a big old universe that evolves us, or a weak scale that is small enough that if with order 1 Yukawa couplings or whatever, we are not black holes, okay? But it's this kind of anthropic reasoning is seemingly self-evident that it must be operating at some level, and yet it is notoriously difficult to model and assess the dynamics of such a multiverse and what exactly is required for intelligent life, et cetera, right? But it raises a huge concern, so we better just face it, okay? That this kind of thing, these kind of anthropic requirements for hierarchical structure, maybe they undercut the hierarchy mechanisms that I just went through, okay? Just taking away all of that good stuff, right? Okay, so before I get back to that, I'd like to say, what could we even hope to do? We seem to be dominated by giants here, these things that might be playing out, these scalars that might have masses themselves of order, the gut scale or something, are nevertheless playing out on these vast scales and determining our crummy lives, okay? How are we supposed to even figure out anything experimentally, okay? So just to say never say never, okay? So when the hobbits get in trouble, there may be help from the sky, okay? So a couple of the speakers, including Juan, had mentioned cosmological collider physics. I just want to give a sense that we are not alone, we little foot soldiers. So we're part of a bigger coherent operation, and we'll figure it out. Okay, so in this picture, all I'm showing you is that during inflation, there is particle creation will take place where the MC squared of the particles is going to be comparable to inflationary energies. And I'm going to be sloppy deliberately about exactly what I mean, but I do mean it's way up there, okay? So you can produce incredibly heavy particles. If those particles then decay or annihilate, if they have preserved quantum numbers, if they decay or annihilate into inflatons, the central importance of the inflaton is it's a clock. It's the clock that tells you when reheating is supposed to start. But inflaton fluctuations mean that the clock is not synchronized between here and there, so that the reheating surface looks ripply like this. And that ultimately turns into the inhomogeneities that you and I are, okay? So it turns into galaxies, and it turns into the fractal structure of the CMB and so on, okay? So when we look at the energy density today in large-scale structure or the CMB or whatever, we are secretly, among other things, if we can get rid of the other things, we are looking back into the past at this kind of physics, okay? So it can show up in so-called non-Gaussianities or 3 or higher point correlators of the energy densities. And if you Fourier transform something like that, it's a function of 2 momenta. So K1 over K3, for example. And that's what's being plotted here. I'm using a picture which I think makes it maximally optimistic, maximally visible to the naked eye. If you plot things like this, what you're really seeing in the 2 colors are literally the wave function of this particle going from creation to decay. And it's oscillating because of the different e to the IMT, the energy in the frequency of oscillation is showing up as a statistical correlator on the sky, large scale structures, say, okay? And different masses oscillate differently. So you're able to measure the mass of the particle that you've created and look at the kinds of scales that you could hope to get to, okay? So this is an incredible, both mathematical, experimental, and sort of physics, both challenge and opportunity, and it's going on at the moment. People are looking into all of those aspects. But what could you hope to learn? One is there really may be ways to test the fate of the standard model and what happens to it at these incredible scales that really bear directly on the hierarchy problem. I don't want to go into that, just with regard to the things that I was telling you about, the controllers. Maybe you would be able to create the controllers in this kind of inflationary process, and maybe even diagnose its potential, so that in principle you could say, oh, this is the kind of potential that has multiple minima. So it's at least consistent with the idea that there are multiple minima which then play out over a super horizon scales and create a landscape. Okay, so there's at least a scientific way to move forward. But I also want to say, coming down back to earth, that there is a sort of, I don't hear this said very often, so I'm going to say it. There's kind of potentially, and very likely, a symbiotic relationship between anthropic principle and the mechanisms we've talked about. It's not one or the other, it's both, okay? For example, go back to this proton mass. Yes, we do need the proton to be much smaller than the Planck scale so that we're not all black holes. Okay, that's an anthropically obvious fact. On the other hand, here is this beautiful mechanism, and don't tell me this is not the truth, okay? Obviously it's true. There's no contradiction between needing to have light protons and having a mechanism, thank you, and having a mechanism that enforces it, okay? So I want to, my slogan, even if the anthropic constraints imply that there are some end goals that have to be met, mechanisms can nevertheless provide an efficient means to realizing those ends in a multiverse, okay? And we can talk about it later, but it gives rise to my first pass, just my first pass version of what to do on the ground where we all live. And that is, to hell with the anthropic principle. That's just my first pass, by the way. And to hell with the anthropic principle. Instead, fully explore and develop theories and experimentally hunt for these hierarchy mechanisms. Hierarchies are the 0th order take on particle physics, okay? We can't just say, oh no, it's an anthropic principle. It's going to do all the work, okay? Second pass. The anthropic principle actually may play a very active role with other mechanisms, BSM mechanisms, in giving rise to what we see, okay? So for example, these guys, and this is my paraphrasing of their title because I was on the breakfast theme of coffee and now here's the cereal. And I only have a cartoon to sort of say very quickly the idea, just the bare bones idea, which is if you imagine that there's some modulus out there, in the sense I've described, which has some effective potential, which basically looks like this most of the time, but it gets corrected when there's a small weak scale. It gets corrected so that there's a little dimple of a secondary minimum up here. Then, whereas if it's an unnaturally large weak scale or zero weak scale, the effective potential goes back to here. So in other words, there's an effective potential for a modulus which is sensitive to having a small weak scale. Then, anthropically, if you live in this metastable universe with small vacuum energy, the universe lives long enough, hopefully at least to meet the requirements of evolving people like us. But on the other hand, if you live in this place where there's a more natural weak scale, the cosmological constant is large and negative, only compatible with a short-lived crunching universe. Okay? So that's the anthropic aspect coming in to determine which of those two turns out to be true. Of course, there's this fundamental question of dark matter. It really is a scientific mystery because it's not just a theoretical mystery, it's an experimental mystery. No stone is being left unturned, as you know, to hunt for it in every possible regime. Thank you. There are new experiments in diverse regimes. That's what I'd say. And just, for example, axion dark matter, just one such direction. A lot of the best of these ideas are creative, they're exciting, they're scientifically, totally warranted and justified. And pragmatically, they're kind of a counterpoint to the sort of the mega experiments that take long time scales and so on, that these can be turned over in a shorter time scale and keep the field exciting and alive, I think is wonderful. And really, you should have had a different speaker to tell you more about it because this is my blind spot, okay? But I think that to the extent that new physics underlies the electroweak hierarchy, to the extent that somehow it does, the idea of the thermal relic WIMP dark matter possibility paradigm still stands out. That starting from equilibrium at super high temperatures, the WIMPs annihilate the weakly interacting massive particles related somehow to TeV scale physics, annihilate in the early universe, and back of the envelope give you a relic density today, which is compared to what we actually see. If you just plug in the idea that there's new physics where at the TeV scale with sort of weakish couplings, this seems to give the right answer. Okay. Now, it's a very sloppy thing. If you even change things by a factor of 2 here, you'll say, what do you mean right answer? It's off by a factor of 100. In a logarithmic sense, it gives the right answer. And that's amazing if you just realize this is energy density to the 4th. It can a priori vary over gazillions of orders of magnitude. And this back of the envelope thing is sort of getting it ballpark right. That's the WIMP miracle. I take it seriously. I know that you've seen lots of exclusion plots. I'd love to show you one, but I don't know how to read exclusion plots. So all I'm saying is there's plenty of options. For example, even the dumbest thing, Higgsino dark matter, is not excluded, okay? But then there's that other matter, baryogenesis, us, okay? The hell with dark matter. Well, put it together and you find there's a kind of unhierarchy problem. It's absolutely mind-boggling to me. I say it at lunch every single day with the gang, that rho dark matter is only order 1-ish rho baryon. When you look at the different mechanisms that are often invoked for producing these two types of matter, it is absolutely a priori ridiculous to think that they should come out that close, okay? So I can't take that out. I can't throw that out of my head and work on one or work on the other. I have to only think of them together. For me, I'm giving you my personal view, as I said. So it suggests, of course, that there's some sort of common or unified origin. This beautiful idea of asymmetric dark matters, playing to that, thank you, is trying to play in that direction, where basically you're trying to say that the dark matter carries baryon number of a general type. So it's exchanged between us and the dark sector. But attempts in this direction to try and find the reason for the comparableness of these two types of energy density typically give up the WIMP miracle. And so my own view is, I think I'd like it all, okay? So can we not make baryon asymmetry more like the WIMP miracle? And you can. You just have to do this, which is to say, have something that should have turned out to be dark matter by the usual WIMP dark matter mechanism. But then at the 11th hour, it decays into baryons in a CP violating and baryon number violating way. Then it should, up to modest factors, basically turn into rho baryon. So you've inherited baryon asymmetry from a kind of WIMP dark matter freeze-out mechanism. It has a very exciting experimental impact because in order to decay only after it freezes out, such a WIMP would have to have a decay length of bigger than a centimeter, a macroscopic decay length. So if you produce these WIMPs at colliders the way you hope to produce dark matter at colliders, it would not be missing energy, or it may not be missing energy. It just may be a particle that decays macroscopically away from the interaction point as a so-called long-lived particle, or LLP, a spectacular kind of signature to look for. And recently there's been work on trying to then incorporate this WIMP baryogenesis with the asymmetric dark matter, and it sort of works at a reasonable level. My own, I'll tell you later if you want, but I hope for an even more satisfying explanation. Thank you. Okay, so I will just say there is something I would call food for thought here. Just to get back to this question of, so let me just say, in the MSSM, it is possible to realize WIMP baryogenesis within the R parity violating option for supersymmetry. And it's got a kind of split supersymmetry structure where the squarks being heavy make the gauginos have long lifetimes in their decay, and with R parity violation, they may actually decay into baryons asymmetrically from antibaryons and actually be the WIMP of WIMP baryogenesis. But when you look at a spectrum like this, you would say, why is the hierarchy problem not being perfectly solved? Why is there a little hierarchy problem? Why haven't I seen supersymmetry yet? Why haven't I seen these quarks yet? After all, the spectrum could have looked more like this, where everybody is there and everybody's already discovered in some alternate part of the multiverse. But notice here that between these two spectra, this one has successful baryogenesis. In this one, there is no successful baryogenesis because the WIMP needs to decay only after it freezes out. Here it decays before it freezes out, okay? So this question that naturalness guides everything is not true. This anthropic requirement of baryogenesis is surely playing some role, but it's not like naturalness does nothing. It's not completely either or, and I call this possibility frustrated naturalness. Okay, I'm just going to say this very fast because I'm 2 minutes over time. I'll just show you the pictures. Everybody, if you think about it for only 1 second, gauge fields and charge matter obviously partition into sectors, which are gauge coupled to each other, and other sectors gauge coupled to themselves, but they don't need to be gauge coupled under each other. Okay, so necessarily this grammar of gauge theory has within it the idea of self-interacting but isolated sectors. Okay, and after you Higgs some of these groups, then they might fragment further, and each of these sectors looks to the other like a ghost. Okay, that's exciting, but that's what they'd look like. Plausibly, these other sectors have their characteristic scale comparable to our characteristic scale, the weak scale. That's why I'm calling them parallel sectors. For example, in gravity-mediated SUSY, the other sectors may have their analogs of electroweak symmetry breaking, Higgs sector, Higgs vevs, given by the radiative symmetry breaking in terms of their other sectors' superpartner masses. But in gravity mediation, all of these are given in terms of the universal gravitino mass, so that the other sectors and us may share comparable sort of scales. So it would be clearly very exciting to discover these other sectors. We are not completely isolated. We live in, these are continents, but there's an ocean of gravity between them, possibly Higgses or axions or moduli that communicate between the sectors. There are recent ideas that build on ancient ideas. For example, these other sectors having their own stars, mirror stars that one can hope to look for. These other sectors or self-interacting dark matter and dark radiation may play a role in the current H0 tension of cosmology. From the collider point of view, there's the possibility that there's a very small cross-section to break out of our sector into these other sectors. But if the particles you produce out here then decay back to the standard model also very weakly, then they'll decay back with long lifetimes and therefore be some of these spectacular long-lived particles, okay? So there's a way of probing this kind of physics more generally at colliders. Okay, I'll just say this, I won't even explain it, but if the other sectors share our properties, they are in some sense partial clones, thank you, partial clones, then they can help technically solve the little hierarchy problem. Or if there are just a lot of these other sectors that round roughly ballpark the weak scale, then they may also explain why we are a little bit fine-tuned, why there's a little bit of a hierarchy problem, by just having many throws of the dice. If you throw 3 dice many, many times, you're guaranteed to get 3 sixes, okay? So now, there are some technical issues in making that idea work, but that's the idea of naturalness. Okay, I'll just say this and stop. In some sense, there are 2 ghosts that are special. The last ghosts to separate themselves from the world of the standard model in sort of cosmic time are the neutrinos. And they have a unique possible, by being ghostly, they have unique astrophysical and cosmological power. They may be portals to other sectors, and they are part of the flavor puzzle. So their data on that is important. The first ghost to depart as we move down in energies is, of course, gravitational waves. They stop talking to us very early on, and yet they are a kind of light that can penetrate where ordinary light cannot in the early universe. And they could be produced by things like phase transitions, and the spectrum of those gravitational waves from these phase transitions may give us a sense of what the high energy physics that gave rise to the phase transition is. Great. Last but not least, there's dumb luck. And, but even that has a program of clearing the weeds so you can make a discovery even if you don't know what's coming, okay? Here's where I'll end. That's it. Really, I should have started with this. We live in this ecosystem as phenomenologists, and it's very important that we do all of these things. It's not pick and choose. Do all of these things, but we have to be canny about how we find our way, like stepping stone to stepping stone, so that we can reach our highest ambitions here. And that's something that requires a separate discussion. Okay, thank you.
Thank you very much, Raman, for this really nice talk. Questions? Nathaniel.
This is going to start out sounding like a comment, but I promise it's a question. So, 20, 30 years ago, when phenomenology and formal theory were closer, I think there were a lot of interesting developments in formal theory or that co-developed with phenomenology. And that gave us a lot of interesting sort of building blocks for approaching the problems of phenomenology. And of course, then the LHC happened, and many of the simplest of those building blocks didn't seem to be realized in nature. And so if I can offer a friendly critique of the vision you've told us, is that it takes those blocks and it rearranges them in new ways. So that's very interesting and gives us new places to look. And so that's great. But I guess my question for you is, we also have heard this morning of interesting and new developments in formal theory that are much more recent. So, here I'm thinking, for example, of Xu Heng's nice talk about generalized symmetries is a good example. We'll also hear about new developments tomorrow. And so do you feel like there's a role for any of those new developments in formal theory, which are very different building blocks? Do you think there's a place or a role they can play in phenomenology as well?
Yes, and yet, I think it is useful, even in a klutzy, clownish way, to take mechanisms that we do see in formal theory and try and putz around with them, as I know even you do, to try and find ways in which they could make their way into the phenomenological world. And my memory, being old enough, was in the 90s when D-brains were being described and so on and so on. And some of us phenomenologically minded people were listening. And it was a kind of like, what a strange thing to imagine living on brains and having this have anything to do with something experimentally measurable. And yet, I think it has borne fruit in many ways, even as far as the flavor problem and so on. It's been very fertile. So I think there is room for that to still happen, but nothing leaps out at me immediately as being ready for prime time. It's not like the second Susie is coming or something like that. So, but keep trying, because something that looks really like only a theorist who is desperate for a job would work on that may turn out to be in 10 years like one of the, the great ideas. Yeah.
Any question on Zoom?
We've got a hand from Noah Brayali. Noah, if you want to unmute and ask your question.
Sure. Great introduction to the desperate theorist looking for a job. I'm thinking about how we might add a question mark. Notice in the middle of the slide here, there's a room for a mega collider. One of the colliders that people are talking about is the mega collider. Wondering if you might phenomenologically might comment, if you can hear me. Yeah, my comment on this connection of maybe searching for a CT charge conjugation time reversal breaking signature using a mu plus mu minus storage ring. Let's say that there is some new physics there. It might be breaking this combined symmetry of charge conjugation and time reversal if, say, it's coming from axions in the dark matter halo of the galaxy.
Nathaniel, did you you want to repeat that question back to me?
I'm not sure. I'm not actually sure I got that. So unfortunately, Noah, your volume is breaking in and out. So we've been picking up and losing you.
I think you can hear me now. Maybe it's better now.
Yeah. Why don't you give it one more shot?
Okay, thanks. So the question has to do with muons. So in the middle of the slide, there's a comment about a mega collider. We had a meeting last week. Nathaniel was the keynote for theory, talking about mu plus mu minus. He's a muon smasher guy. He knows all about it. He can tell you about it. And the question is, can we connect it with this beautiful work with muon spin that was done in the Fermilab last year, and think about using mu plus and mu minus and their comparison to look for a time reversal breaking, well, say CT breaking signature in the spin precession when you try and measure the beam energy or something like that, like you did at LEP for the electron positrons to get the Higgs the Z boson precision measurements. Maybe we can connect it there and think about using our colliders as haloscopes, where we're grabbing the dark matter rather than making it. Not bringing sand to Santa Barbara, but instead using the dark matter that's there to look for, time reversal breaking signatures. Let's say the dark matter is an axion.
So the closest I'm going to come to an answer there is the idea that dark matter can actually give rise to effectively, CP violation is sort of the idea behind, was it the Casper experiment, where dark matter would be axion waves, but the axion waves would push you away from this CP invariant vacuum of the standard model at rest. And you could then do time dependent, the analog of neutron EDMs, but or atomic CP violation, but for time dependent effects. That idea is reasonable. I'm not sure whether a mu plus mu minus collider is the place to get the kind of sensitivity that would compete, but the principle of having dark matter come through the room and break a fundamental symmetry in a time-dependent way is a great idea, and I'm all for doing good experiments on that front.
All right, thank you very much. So let's thank Raman again.